4.6 Conclusion. This chapter has focused on the use of ordinary least squares to estimate the intercept and slope of a population regression line using a sample of n observations on a dependent variable big Y and a single regressor big X. The sample regression line, estimated by ordinary least squares, can be used to predict big Y given a value of big X when beta sub 1 is defined to be the causal effect on big Y of a unit change in big X, and the least squares assumptions for causal inference. See key concept 4.3. Hold then the ordinary least squares estimators of the slope and intercept are unbiased, are consistent, and have a sampling distribution with a variance that is inversely proportional to the sample size n. Moreover, if n is large, then the sampling distribution of the ordinary least squares estimator is normal. The first least squares assumption for causal inference is that the error term in the linear regression model has a conditional mean of 0 given the regressor big X. This assumption holds if big X is randomly assigned in an experiment or is as if randomly assigned in observational data. Under this assumption, the ordinary least squares estimator is an unbiased estimator of the causal effect beta sub 1. The second least squares assumption is that open big X sub I and big Y sub I close are independently and identically distributed, as is the case if the data are collected by simple random sampling. This assumption yields the formula presented in key concept 4.4 for the variance of the sampling distribution of the ordinary least squares estimator. The third least squares assumption is that large outliers are unlikely. Stated more formally, big X and big Y have finite fourth moments, finite kurtosis. This assumption is needed because ordinary least squares can be unreliable if there are large outliers. Taken together, the three least squares assumptions imply that the ordinary least squares estimator is normally distributed in large samples as described in key concept 4.4. The results in this chapter describe the sampling distribution of the ordinary least squares estimator. By themselves, however, these results are not sufficient to test a hypothesis about the value of beta sub 1 or to construct a confidence interval for beta sub 1. Doing so requires an estimator of the standard deviation of the sampling distribution, that is, the standard error of the ordinary least squares estimator. This step, moving from the sampling distribution of beta sub 1 hat to its standard error, hypothesis test, and confidence intervals, is taken in the next chapter.